Hello everyone. Today we are going to discuss about the topic electrostatic potential and capacitance, NCERT section 2.1 to 2.5. Disclaimer: the images, text and other materials used Disclaimer: the images, text, and other materials used in our presentation are for educational purposes only. We respect the intellectual property rights of the original creators and owners. If you are the owner and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the content immediately. Please note that parts of the content may have been generated using generative AI, which is experimental. So it is the index of the topics that we are going to discuss today. So first of all, introduction of electrostatic potential, energy and potential. After then electrostatic potential, then potential due to point charge, then potential due to electric dipole, and then at last potential due to a system of charges. Introduction. What is the objective of our today's topic? That is understanding potential energy in electrostatic force and field. So the concept, you have already heard about this term potential energy in your 11th class in chapter work, energy, power and gravitation. So today that potential and potential energy we are going to discuss about is the analogous of potential energy that you have learned in the gravitation chapter. That is clear analogous. The thing that is different from that part is there in gravitation chapter we were assuming mass, and here we are going to take charge at the place of mass, and formula are also very similar that we know about the potential energy and potential. So the concept of potential energy in electrostatics follows the same principle introduced in your chapter 5 and 7 of class 11th for conservative forces like spring force and gravitational force. When external work is done against these forces, it gets stored as potential energy. So here is a diagrammatical representation that this charge, this capital Q charge, is known as source charge. That capital Q is known as source charge, which produce the electric field. In gravitation, we took a source mass that creates gravitational field, and similarly in electric field, this is capital Q which creates the electric field. This small q is the test charge which we are going to move from between 2 points in the electric field of this source charge. This is test charge. So figure 2.1, a test charge that is small q, which is by default we are taking the charges positive. So this test charge is moved from point R to the point P against the repulsive force, because both these charges are positive. So there is a repulsive force between these two charges. Against the repulsive force on it by the charge capital Q, which is greater than 0, that is positive, placed at the origin. So Coulomb force between them being a conservative force. We know that in gravitation, gravitational force is conservative force. What is meant by conservative force? The force which depends only on initial and final positions. So this Coulomb force is also conservative force, similar to gravitational force, with inverse square law dependence, allows us to define electrostatic potential energy for a charge in an electrostatic field. Consider a charge Q at origin creating an electric field E. As I have already mentioned, this is the source charge which create the electric field E, and a test charge small q being moved from R to P. from here to here against the repulsive force between the two charges. Okay, the two key assumptions which we are going to made here. First assumption is test charge small q is very small, infinitesimal small. A test charge q is small enough not to disturb the original configuration. Means small charge q, test charge, should be that small, it should not disturb the original configuration of the source charge. Means it do not affect the electric field of source charge as much. So this test charge we are going to take very small. Another assumption is external force F external exactly counters the electric force, that is Fe, electrostatic force or electric force. What does that mean? This assumption is very important. It means that we are going to move the charge from R to P very slowly. Why slowly? Here it is also written moving the charge at infinitesimally slow constant speed. Why constant speed? If we are going to move the charge with fast speed, means if we are going to change the velocity of the charge, then there is a change of kinetic energy. We don't want here the change in kinetic energy because we want the whole work done to be converted into potential energy. If we consider change in kinetic energy here, we have to take kinetic energy change also in the equation. That will make it complex. So we are going to move the charge from R to P very slowly so that there will not be any kinetic energy change, and net force on that charge is 0. What does that mean? That external force external exactly counters this electrostatic or electric force, which means these two forces are equal and opposite, such that net force on the test charge is 0 and it moves with constant speed. There is no change in the velocity, hence kinetic energy. These are the two assumptions. Then the work done by the external force is, then we also know, we have seen this type of expression in gravitation also. What is this? F external dot dr. Dr is the small distance traveled by this charge, and this is, we are integrating this small work from R to P. This is the total work done from to move a charge from R point to P point. This is the total work done. This is the small work done, and we are integrating it from R to P. Since we have assumed that external forces exactly counters the electric force, it means this electric force is equal and opposite of external force, which means we can write it as minus Fe dot dr from integrating from R to P. Mark it as equation 2.1. And this work done is against electrostatic repulsive force and gets stored as potential energy. So we are moving the test charge against the electric force of source charge. So force between them is repulsive. So we have to do the work to overcome this repulsion. So that work done is stored in the form of potential energy. Okay. So I am repeating these assumptions again. So first assumption is we have to take the test charge Q very small because we don't want it to interact with the source charge. So it should not disturb the original configuration. And second, which is most important assumption here, is that we are moving that test charge from R to P very slowly. Why slowly? Because we don't want any change in kinetic energy here, because we want total work done to be stored in the form of potential energy only, so that to avoid the complexity of the equation. If we move this charge with fast speed, it will change the velocity. final velocity and initial velocity will become different, and there will be change in kinetic energy also. So work done will be equal to change in potential energy plus change in kinetic energy. We don't want that kinetic energy portion here to avoid the complexity. So we are moving this charge at very infinitesimally small constant speed. For constant speed, what must be done to make the net force at this charge 0, which means external force that we are applying should be equal and opposite to this electrostatic force. I hope you understood. So this work increases the potential energy by delta U equal to UP minus UR, means potential energy at P minus potential energy at R, which is equal to work done to move the test charge from R to P. So this del U, this UP is greater than UR. Why? Because we are moving the test charge against the repulsive forces. So potential energy at P is greater and potential energy at R is smaller. And this delta U will result in positive potential energy. That is work done to move test charge from R to P. So we have to do the work against the electrostatic force. So this potential energy will be positive. Okay, important characteristics of the electrostatic potential energy. Okay, since the work done or force are conservative here, so work done depends only on initial and final position, not the path taken, proving its conservative force. Also, second thing, potential energy is defined up to an additive constant. What does this means? And meaning only potential energy differences are physically significant. Okay, in gravitation chapter, in NLM or in straight line motion, we have discussed that we have assumed the reference point where potential energy is 0 to be the surface of Earth. In gravitation chapter, we assumed the reference point to be the center of Earth. That is the concept which is applying here. Reference point. Potential energy at a point only depends on the reference point. Means which point we are taking the reference. Surface of the Earth or center of the Earth. Surface of any charge or center of any charge or any other point we are taking reference. Potential energy depends on that point. Means potential energy alone is not a physically significant term. Physically significant term is potential energy differences, because it will remains constant. Rather, it doesn't depend upon reference point. Means what does that mean? Up to an additive constant means if we are taking at any point potential energy 2 joule and on another point we are taking 5 joule. Difference between 2 points potential energy difference is 3 joule. But the difference is if we are taking the another reference point, due to which the potential energy at both these points changes. We are taking the potential energy at 2 joule where a point A, suppose A point where potential energy was 2 joule now become 3 joule, and the potential energy was 5 joule at another point and now it becomes 6 joule. Difference remains same. Difference remains 3 joule. Means we can change the reference point, due to which potential energy at individual points changes, but potential energy difference remains constant. So potential energy difference are physically significant terms, not potential energy at a point. Now, what we are taking reference here now? Choosing 0 potential energy at infinity. Now we are taking 0 potential at infinity. This is the reference. We are taking references. In gravitation, we took potential energy as 0 at center of the Earth. Now we are choosing 0 potential energy at infinity. So reference we can define only. But the physically significant term is potential energy difference, which will remains constant either if the reference point changes. Now, work done to bring the charge from R to P was WRP. Now, work done to bring the charge from infinity to P point is UP minus U infinity, means potential energy at P point minus potential energy at infinity. Now we are taking potential energy at infinity is 0. So work done to bring the charge from infinity to point P is stored in the form of potential energy, which is equal to potential energy at point P. And this is the definition of potential energy at any point. So potential energy at any point, this is the definition of potential energy. Potential energy at any point is defined as the work done by external force that we are applying in bringing charge Q from infinity to that point against the electric field of any charge configuration. Simple. What is potential energy now? Work done by the external force to bring a charge from infinity to any point in the electric field of any charge configuration is the potential energy at that point. Now, the potential energy of test charge Q is any general static charge configuration is defined as the work done on the charge Q. Okay, work done on the charge Q is stored in the form of potential energy. This is we all know. Since the force at any point is QE, we know that force at any point is Q into electric field, where E is the electric field due to given charge configuration. This work is proportional to Q. Now this work is proportional to Q, so we have to find the term that is independent of Q. Okay, for convenience we divide the work by charge Q to get a quantity independent of Q. So we want a quantity that is independent of Q, and for this we have to divide the work done by Q charge, and this will result in potential. So this is the charge configuration we are taking here. This is Q2 charge, Q3 charge, Q1 charge, and Q charge and Q4 charge. These all charges producing electric field, that is E, and force at any point in the electric field is QE, experienced by this Q. Okay, and we are as the work is proportional to Q, so we have to find any quantity that is independent of Q. So we have to divide the work done by Q. Okay, figure 2.2, what it is representing: work done on a charge Q by the electrostatic field due to any given charge configuration is independent of path, which I have already mentioned that it is conservative force and work done by these force is conservative, so it only depends on these R and this P point. It doesn't depend on path taken, whether you are coming from R to P through this path, it will depend only on P and R. Okay, the work done per unit charge characterizes the electric field of the charge configuration, introducing concept of electrostatic potential V. Okay, work done by external force. Now this is the main thing. What is the potential? Potential is work done upon charge, that test charge. Work done by external force in bringing, now the definition changes. What is the definition of potential energy? Work done by the external force to bring a charge from infinity to any point in the electrostatic field is the potential energy at that point. Now at the point of charge, at the place of charge, we will replace it with unit positive charge. Definition remains same, but we are replacing the charge with unit positive charge. Work done by external force in bringing a unit positive charge from point R to P. because we are dividing it with Q. So the charge is replaced with a unit positive charge. So definition of potential becomes work done by the external force in bringing a unit positive charge from point R to P. Okay, so this will become Vp minus Vr, which is equal to Up minus Ur. What is this? Up minus Ur is the work done to bring a charge from point R to P, and upon Q this will result in potential difference between 2 points, where Vp and Vr are electrostatic potentials at P and R respectively. The potential difference. Now similarly, potential energy was only significant when there is a potential energy difference, not absolute potential energy. Similarly, potential also has physical significance. Potential difference has physical significance rather than absolute potential. Absolute potential at any point has no significance, because potential and potential energy both depends upon reference we are taking. It depends upon which reference we are taking. We are taking zero potential at surface, at center, at infinity. It depends on that reference. But the potential difference has physical significance. It remains constant. It is independent of reference chosen. When potential at infinity is chosen as 0, then equation 2.4 shows that electrostatic potential at any point equals the work by an external force in bringing a unit positive charge from infinity to that point. That is the definition again. That is similar, same expression again. Now we are assuming this Vr to be 0, because potential at infinity is chosen as 0. So we will put this point at infinity and it will become Vp equal to Up upon Q. Okay, so to obtain one more way to find the work done per unit charges, to obtain the work done per unit charge, we should take an infinitesimal charge delta Q, very small charge. This means very small test charge. Obtain the work done delta W, you have to obtain the work done like this and then divide it with that charge. Similar thing is explained in this line also with different notations. Thing is similar. To find the potential difference, what you have to do, you have to find the work done to bring a charge from any point to another point and then divide it with the test charge. Now to find the electric potential due to a point charge. The electric potential at any point P due to a positive point Q located at the origin is defined as the work done. This is the definition again, is defined as the work done in bringing a unit positive charge from infinity to point P against the repulsive force. Now there will be a diagram, you will understand better. I will explain this again. Now this is Q. Now see the diagram, this is Q, this is source charge. Here +1 coulomb, this is unit positive charge that we are taking test charge. That is, now in potential we are taking test charge as unit positive charge. Now potential due to this source charge at this point is absolute potential. Understood? Potential at this point due to this charge is absolute potential. But the potential difference between these two charges is potential difference. Absolute potential has no significant physical significance, because if we are taking potential at this point is 0 or at infinity to be 0. So this absolute potential depends on the reference point, whether we are taking the potential at infinity to be 0 or at this 0 O point to be 0. But the potential difference doesn't depend on reference point. It has physical significance. Okay, Now we are going to do the derivation part of this concept. Okay, with the help of diagram. This is the test charge that we are moving from infinity to that point P. We are going to bring that unit positive charge from infinity to point P at this point. Okay. Now what this figure represent? Work done in bringing a unit positive charge from infinity to point P against the repulsive forces of charge Q is the potential at point P due to charge Q. Okay, this is the definition. What is the definition? I am again repeating what is the definition is work done in bringing a unit positive charge. Unit positive charge means plus 1 coulomb from infinity to that point P is the potential at P. Okay. Now, in the derivation, what we are going to do, we will first find the force as this P dash, any P dash point between infinity and this P. Then we are going to find the small work done through this interval. And then we will integrate it and find the potential. This is totally the derivation part. Okay, since work done is path independent because the forces are conservative, we choose to move along the radial direction. So we are not assuming any other path. We are choosing only radial direction. At the any intermediate point P dash, any intermediate point P dash, the electrostatic force on a unit positive charge is, what is the electrostatic force formula? F is equal to Q into Q by R square and also multiplied by the constant 1 by 4 pi epsilon naught. So this is 1 by 4 pi epsilon naught Q into small q here is plus 1 coulomb because we are taking unit positive charge upon R dash square, and this is the direction of the force where R cap is the unit vector along the OP dash. Okay, with the help of this diagram, we are finding the force, electrostatic force on this test charge at this P dash point. So due to this Q, between this plus 1 coulomb and this Q, electrostatic force is Q into 1 by 4 pi epsilon naught, and distance between these two charges is R dash square, and the direction is R dash cap, means the unit vector along this direction. Now, figure 2.3, what it is representing? Work done in bringing a charge, a unit positive charge. Okay, again that similar image. And mark this equation at 2.5. Now, work done against this force from R dash to R dash plus delta R dash is, okay, what is the work done to move this charge from P dash to this point, P dash to this point through this small distance delta R dash? Work done is Q by 4 pi epsilon naught R dash square into, this is force into displacement. What is the displacement? Delta R dash. Why is this negative sign? Because we are moving against the electrostatic force. And also, when this delta R will be negative, work done will be positive. Yes. Negative sign appears as delta W is positive when delta R dash is negative. Why delta R will be negative? Delta R will be negative if we are moving towards this charge. Then final distance minus initial distance will be negative. Means we are moving from here to here. So distance will reduce. Final distance will be from this O to this. And initial distance was from this O to P dash. So final minus initial will be negative. This delta R dash will be negative. If we are moving in this direction, then work will be positive. If we are moving in opposite direction, then delta R dash will be positive and work will be negative. means delta r dash, when delta r dash will be negative, when we are moving towards this charge, means the distance from this charge is reducing, then delta r dash will be negative and the work will be positive. And if we are moving in this direction, then delta r dash will be positive and work done is negative. Now, total work done by the external force is found by integrating from r dash equal to infinity to r dash equal to r. Now, we are moving with the definition. So, we will integrate from infinity to that point P. Means we are integrating from the, now we have calculated a small work done through small distance delta r dash. Now we will calculate the total work done from infinity to point P. So integrating from infinity to that point P, which is at a distance r from the capital Q. So Q by 4 pi epsilon naught r dash square into dr dash. Delta r, we are not taking delta r because delta r is somewhat large interval. Dr is very small interval. For integrating, we have to take very small interval. So there is a shift from delta r dash to dr dash. So we are integrating from infinity to r. So after integration, this is integration part, and putting these values, we will get this final result. Mark it as 2.7. And this is the formula for potential, because the charge here small q we are taking as 1 coulomb. The potential at P due to charge q will be equal to this. This is the final result we got. Potential at any point is q by 4 pi epsilon naught r. R is the distance from the source charge. This equation holds for both positive and negative charge. For negative charge, V is negative, meaning the work done by external force per unit positive charge is negative. This Q will become minus Q and potential will become negative. This is equivalent to positive work done by the electrostatic force as expected, since the force is attractive for negative Q. This equation ensures zero potential at infinity. So we have assumed a zero potential at infinity, already mentioned. We are taking from infinity to r. So zero potential we have mentioned at infinity. Now, what is our motive? To find the variation of E and V with distance. We have already seen the variation of E with the distance. Now we are comparing with potential. Electrostatic potential, which is directly proportional to 1 by r according to the equation. And electrostatic field, what was the electrostatic field? That is q by 4 pi epsilon naught r square. So electrostatic field is inversely proportional to r square. Both vary with distance. One varies with inverse square law. Electrostatic field varies with inverse square law, and electrostatic potential is proportional to 1 by r. So this is the graph of these two quantities. So electric field also decreases as the distance increases, and potential also decreases as the distance increases. So this is a figure, variation of potential V with R, that is blue curve, and field with R, that is black curve, for a point charge Q. Now one numerical example. Okay, calculate the potential at point P due to charge 4 into 10 raised to power minus 7 coulomb located 9 centimeter away. This is the first part. Second part is hence obtain the work in bringing a charge 2 into 10 raised to power minus 9 coulomb from infinity to the point P. Does the answer depend on path along with which the charge is brought? So firstly, we have to calculate the potential. Then we have to calculate the work done. Now, in potential, we assume the test charge as unit charge, 1 coulomb. Now we have to calculate the work done, which is equal to charge into potential. Potential is charge by, potential is work upon charge, and work is charge into potential. So we have to simply multiply this charge with the potential, and we will find the work done. So what is the, for first part, what is the potential? Q by 4 pi epsilon naught R. What is the Q here? The source charge, 4 into 10 to the power minus 7 coulomb, and 9 centimeter away, 0.09 meter, and 1 by 4 pi epsilon naught value, 9 to 10 to the power 9 Newton meter square per coulomb square. After calculating, it will result in 4 into 10 to the power 4 volt. This is the value of potential we got. Now we have to find the work done in bringing a charge of this from infinity to point P. So we will simply, this is the relation of work and potential. Work is equal to Q into V, equal to 2 into 10 to the power minus 9 coulomb into that potential we have calculated earlier. And we got the work done 8 into 10 to the power minus 5 joule. Now, the answer to this question, does the answer depend on path along with the charge is brought? So we already discussed that this is the work done by conservative forces. So it doesn't depend on the path. It only depends upon initial and final position. No work done will be path independent. Any arbitrary infinite similar path can be resolved into perpendicular displacements, one along R and another perpendicular to R. The work done corresponding to the later will be 0. Okay. Now, what is our next motive? To find the electric potential due to a dipole. Now, we have found the electric field due to dipole. Now, we are going to find electric potential due to a dipole. An electric dipole consists of two charges, as we already know, that plus Q and minus Q, and they are separated by distance 2a with 0 total charge. It is characterized by a dipole moment vector P with magnitude Q into 2a, pointing from, what is the direction of dipole moment vector? From negative charge to positive charge. This is the dipole. From negative charge to positive charge, this is the direction of dipole moment vector. And we have to find the electric potential at this point P due to this electric dipole moment. So this is the center of the dipole moment. This is the center of the dipole. And from center, the distance, the position of this P point is R, and this is the position vector directed towards this P point. R1 is the distance of this P point from plus Q charge, and R2 is the distance of this P point from minus Q charge. And this is the 2a, that is distance between these two charges. And this is the angle between the dipole moment vector and the position vector, theta. Okay. Now this figure 2.5, quantities involved in the calculation of potential due to dipole. Okay, the electric field obeys, as we know, electric field obeys and electric force also obeys superposition principle. Since potential is related to the work done by the field, electrostatic potential also follows the superposition principle. Okay, so what is the superposition principle? That the potential at this P point is the sum of the potential due to this positive charge and potential due to this negative charge. This is the superposition principle. The potential due to dipole the potential at P point due to dipole is the sum of potential due to individual charges, that is plus Q and minus Q. So that is V equal to 1 by 4 pi epsilon naught Q by R1. And why this negative sign? Because one charge is negative. So Q by R1 minus Q by R2. So mark this equation as 2.9, where R1 and R2 are the distances of the point P from Qn minus Q. These distances. Okay, so potential due to this positive Q charges 1 by 4 pi epsilon naught Q by R1, and this charge is minus Q by 4 pi epsilon naught R2. So by adding them, this is the result, and mark it as 2.9 equation. Now what we have to do, we have to make a perpendicular from this P point at this. We will extend this dipole in this direction and make a perpendicular from P point here. Okay, so perpendicular, make a perpendicular here, and like this. Then assume it as this distance as x, and assume this distance as anything you want to assume. Then after applying the geometrical terms, you can find this R1 and R2. You have to find this R1 and R2 in the terms of A and R by applying the Pythagoras theorem in this triangle, and after you can do in this triangle also. You have for this R2 you have to make the perpendicular here, and after applying in this triangle you will find you'll find this geometrically. Okay, after means you have to play with the geometry here, and you will find this R1 and R2. Okay, so by geometry, this R1 square results in R square plus A square minus 2AR cos theta, and this R2 square results in R square plus A square plus 2AR cos theta. You can do it later by solving it using the geometry of this diagram. Okay, after we can take R much greater than, now we are taking assumption here of short dipole, means the A should be much less than the distance of point P from the dipole, means that P point is very large, at very large distance from the dipole, or we can say that the dipole is very short. The dipole length is very much less than as compared to the distance of the P point from the dipole. We take R much greater than A and retain terms only up to first order in A by R. What is this A by R? Means this distance is the half of the distance between the two charges in the dipole, and this is the distance of the P point from the dipole center. So this is, if we take this very small term and this is very large term, the ratio of these two terms will be very small, and if we take the square of this very short term, it will become even more smaller, such smaller then we can neglect it. So we can take only the first order, means A by R. We cannot take the second order, means the square of this term we will neglect it. Like in this equation, R1 square is R square, we are taking common from here, it will become 1 minus 2A cos theta by R plus A square by R square. Now this will become second order, A by R second order, A by R whole square. So we can neglect this. So this will result in R square 1 minus 2A cos theta upon R. Mark it as 2.11. Similarly, R2 square, we can write it as this, and neglecting the A square by R square term from here also. Mark it as 2.12. Using the binomial theorem. Now we are going to use binomial theorem, and retaining terms, only retaining terms that are first order of A by R. 1 by R1 is equal to 1 by R 1 minus 2a cos theta R minus 1 by 2. And we are reciprocating the equation, means R1 equal to R, we are reciprocating it. 1 by R1 equal to 1 by R 1 minus 2a cos theta by R raised to power minus 1 by 2. And here 1 by R1 equal to, nearly equal to 1 by R a plus 1 plus a by R cos theta raised to power minus 1 by 2. 2.13a equation. Similarly, we can write it here as 1 by R2 nearly equal to 1 by R 1 plus 2a cos theta. Now, after applying the binomial theorem here, this minus 1 by 2 will come here, come in this side, means it will multiply with this term. Minus 1 by 2 will multiply with this term. It will become 2 by 2 cancel out, minus minus plus. Here also it will multiply with this term and it will become 2 by 2 cancel out, plus minus minus. So after applying binomial theorem, binomial approximation, we got the value of 1 by R1 and 1 by R2, which we intended to find. So using equation 2.9 and 2.13, and we also know what is the dipole moment, that is Q into 2A, that is 2QA. We got, after putting the value of 1 by R1 and 1 by R2 in 2.9, we got the value Q by 4 pi epsilon naught 2A cos theta R square, and 2AQ is P. So final result is P cos theta 4 pi epsilon naught R square. This is the potential at point P due to the dipole. Now we also know P cos theta is P dot R, dot product of P vector and R cap, unit vector, where R is a unit vector along the position vector OP. That R, that is the position vector, that R cap is the position vector OP. Now the electric potential of a dipole is then given by 1 by 4 pi epsilon naught P cos theta. We are replacing it with P dot R cap by R square, where what we have assumed, that distance R is much greater than the dipole length. Assumption applied here. This is the final result of the potential due to a dipole. Now equation 2.15 is as indicated approximately true only for distances large compared to the distance size of the dipole. This equation is approximately true for large distances, or we can say for short dipoles, so that higher order terms A by R are negligible. We have neglected this term by assuming that dipole is short or the distances are very large, that point P is very large distance from the dipole. So this is again that condition applied, the formula. So for a point dipole P at the origin, equation 2.15 is however exact. Now some special cases. First case is when theta is 0 or pi, when the charge is at point in the axial line, then V is plus minus 1 by 4 pi epsilon naught, P cos 0 is 1 and P cos pi is minus 1. So plus minus this term. The expression is valid for distances much larger than the dipole size. Again, assumption is applied here. Okay, for this is again that thing. Yes. Second thing, potential becomes 0 on the equatorial plane if theta is theta is pi by 2. If theta is pi by 2, so cos pi by 2 becomes 0. So at equatorial plane, the potential becomes 0. Means equatorial plane is plane at the midpoint of the dipole, plane passing through the midpoint of the dipole, At this plane, the potential due to positive charge cancel out the potential due to negative charge, and net potential at that equatorial plane becomes 0. Then the dipole potential differs from single charge potential in two aspects. It depends on both R and the angle between R and P while maintaining axial symmetry about P. It falls off 1 by R square. Now, potential due to single point charge varies with 1 by R, and potential due to dipole varies with 1 by R square. This is the difference between both these cases. Now, superposition principle, as I have already mentioning again, the potential at point P to multiple point charges, if there are multiple point charges present there, then the potential at P point is the sum of potential due to all the charges present there. Potential at point P due to multiple point charges can be calculated using the superposition principle for a system of charges Q1, Q2, Qn at positions given by vectors R1, R2. This is the diagram. If there are multiple charges present, Q1, Q2, Q3, Q4, Q5, and the distances of these charges from this point P, where we have to find the net potential, is R1P, R2P, R3P, R4P, and R5P. So what is the net potential at this point P due to these all charges? Is the sum of the potential due to these individual charges. Okay, potential at point due to a system of charges is the sum of potential due to individual charges. Means the potential V1 at P point due to charge Q1 is 1 by 4 pi epsilon naught Q1 R1P. Similarly, for Q2 is 1 by 4 pi epsilon naught Q2 upon R2P. Similarly, for other charges, and then we add up all the potentials, we will get the net potential. Like this. Similarly, for charges Q2 and Q3, the potentials are V2 1 by 4 pi epsilon naught Q2 upon R2P. For V3, this, where R2P and R3P are the corresponding distances from P. By superposition principle, the total potential V at P is algebraic sum, not vector sum, because potential is a scalar quantity. Electric field and force was vector quantity. That's because we used vector sum. In superposition principle of electric field and force, we used vector sum because that were vector quantities. Potential is scalar quantity. So we are using algebraic sum of potential by individual charges. So V is the sum of all the potentials due to individual charges. V1 plus V2, so on up to Vn. V equal to 1 by 4 pi epsilon naught Q1 by R1P plus Q2 by R2P plus so on up to Qn by Rnp. So for continuous, if there are not discrete charges present, for continuous charge distribution with charge density rho r, we divide into small volumes. Then for continuous charge distribution, we will divide the whole system into small volumes delta V with charge rho into delta V, and then integrate the contribution to get the total potential. We will integrate the contribution of these small volumes, and then integrating it, we will get the net potential. For a uniformly charged spherical shell, this is the continuous system for uniformly charged spherical shell. Then potential outside R greater than R for outside point is V1 by 4 pi epsilon naught Q by R, where Q is the total charge and R is the radius. Inside the shell, potential is constant. Why? Because the electric field is 0 inside the spherical shell. We also know that in gravitation, gravitational field intensity inside a spherical shell was 0. Similarly, in this electric field inside the shell is also 0, and potential is constant everywhere inside the spherical shell. Okay. So this is all about electric potential at a charge, electric potential at a due to dipole and superposition principle. Thank you.